Hello everyone, thank you for joining us today. I am András Herbai, I'm your host today on this webinar. Just for some practical information, the control panel can be hired with the red arrow button. Questions or messages can be sent with the chat option. At the end of the webinar, I will answer them. As usual, this webinar is being recorded and will be posted on our website and YouTube channel. Today's webinar is about the new features of ConSteel 11 and csJoint 11. The latest version of our structural analysis and design software was introduced at the end of April. Quickly about the agenda. First, talk about the new BIM interface functionalities, what are one of the main improvements in this version. I will show you how can we collaborate with any members of the IFC industry thanks to the new IFC model import and export, and handle parallel Tekla and ConSteel model to visually verify the modifications, deletions and new elements between the ConSteel and Tekla structure models. Then I will introduce you the completely redesigned seismic analysis tool. The new tool is very flexible and transparent. All of the phases of the calculation can be checked and controlled by the engineers. Completely new things is the csPI ConSteel programming interface. With the new csPI interface, parametric model can be built easily and run anytime. After that, I will present some minor new functions such as shear field and the improved frame corner wizard. Finally, the new functions of the csJoint module will be introduced shortly. Okay. So let's start with the long-awaited IFC functions from the new BIM functionalities. So thanks to the new IFC function, you can collaborate with any members of the AIC industry, such as architects, building engineers, etc. IFC import and export function is a very simple to use function, despite of the vast development need. I have to say that ConSteel support the IFC 2.3 IFC frame and handles the object of the IFC building element class, beams, columns, walls, slabs, etc. The imported IFC objects are automatically converted to the relevant native ConSteel objects. I have previously opened an IFC model. This is one of our reference from Romania. And I opened this IFC model in a free IFC viewer. If you select any member of the model, we can check the parameters. We can see this is a IFC member, a generally positioned beam, and contains the sections and the materials and etc. all of the informations. If you go to the ConSteel, IFC import can be started with the File menu, Import and IFC functions. At first, the path of the IFC model must be given. So we can open. Okay. Then we can set the scaling if it's needed with a scale factor or with the original units of the IFC model, so it can be in millimeter, centimeter and meter. and we can move the placement of the origin if it's needed. And of course, the plan of the placement can be set. We can use the 3 original planes, or we can use a user-defined coordinate system if it's needed. If we set everything, the import process can be started with the import button. Okay. The first step of the import is the section and the material conversion. So we have a new conversion function. So you can see. So this is a general functions used for IFC import, Tekla import, etc. So thanks to the new conversion functions, now not just the members but the plates also can be converted to ConSteel members. In our current model we don't have any plate. For the conversion, ConSteel use at first the previously created conversion files you can find. You can load your own conversion files if you have. But as a further step, if it's not available, the file is not available, or ConSteel is not able to find the match, ConSteel try to convert the section according to the geometry properties or the names, and try to automatically convert all of the sections and materials to ConSteel native section and materials. So here you can find all of the the imported members and section names and material names. So this is the origin and this is the converted. If it's needed, you can switch or select another one. And if you want, you can save this conversion selection to a file for later use. And if you click on one of the row, you can see the properties. Okay, and if you click on the continue button, ConSteel start to convert the IFC model to native ConSteel model. Okay, so here you can see the full IFC model is imported to ConSteel, and if we see, we can see the properties. So this is a bar member, reinforced concrete bar member. It is automatically converted to ConSteel bar with the relevant cross sections and material grades. So this is again a bar member with hollow section and etc. So this is the IFC model import. For IFC export, I open a simple 3D model. So this is a simple 3D frame or hole, but it contains not just members but the slab also. So if you go to the file menu, export, you can find the IFC function. If you click on it, you can start the process. It is needed to select the path of the IFC file. Okay, it's okay. We can set the scaling if it's needed. Now I'll leave on default, and we can set also the plane of the placement. And if you click on the export button, ConSteel is export the whole ConSteel model to IFC model. And if you go back to the IFC viewer, you can open the ConSteel model. Here it is. You can see, and not just the member, but the slab also is exported to IFC. Here you can see the type is IFC slab, and the material grade is the selected concrete material grade. Okay, so this is the IFC import and export functionalities. Okay, the next big thing is the Tekla ConSteel change management. For this, I open a new ConSteel model. And I previously opened in Tekla structure a 3D Tekla model. So Tekla import and export function was available in the previous version of ConSteel, but the model update was not available. So if you modify something in the model, we have to restart the import and export process again, and in this case, a completely new model was created in ConSteel and in Tekla, and sometimes it's not the best way. So now with the new functions, if we import a Tekla model to ConSteel and modify something on the ConSteel model, we are able to update the parallel Tekla model. So let's see how is it working. So we have a 3D model in Tekla structures. As a first step, we have to import the Tekla model to ConSteel to create the connection between the two parallel models. But connections can be created with not just the import process, but with the export process also. The parallel Tekla model ID is saved into the ConSteel model. Okay. So the import functions can be found in the File, Import and Tekla Structures menu. So here it is. And if you click on it, on the import dialog, there is some new options. We can decide which part of the Tekla model should be imported. So we can import all of the model or just the selected parts. And also we can import now not just the structural members, but the structural grids also from Tekla structures. Now I select the options, and we can decide which layers or layer should be used for the import. So we can use the Tekla structures layer system. In this case, ConSteel import and used Tekla structures classes as layers in ConSteel. Or we can use one of the previously created ConSteel layers. Okay, now I use the Tekla structures layers. If you click on the import button, ConSteel start the import process. The first step, here you can see on the information field, the first step is to pick the reference point in Tekla structures. So in this case, you have to go to the Tekla structures, and you have to click on select the origin of the placement. And if you go back to the ConSteel, you can see the next step is the conversation. So the conversation process is same as was shown previously during the IFC import. So we have the same conversation dialog. Here you can see the import name, material name, and the used ConSteel name. And if everything is correct, we can click on the continue. And the last step is to pick the reference point in ConSteel. And if you click on it, ConSteel import the whole Tekla structure model to ConSteel. So now we have a 3D model in ConSteel. You can start the design process. You can create new members or modify existing members, or we can create and place structural joints on it. The modified ConSteel model can be exported to Tekla, of course. So we have the same Tekla functions, Tekla export functions. So we can export all of the members, selected members. You can export the actual structural grid. You can export the connections. And in this case, we have two export settings. We can overwrite the existing Tekla models, or we can add the models or the selected parts to an existing Tekla model. But now I would like to show you how the update process is working in ConSteel. So for this, let's do some modifications on the model. At first, so let's modify some sections on the model in ConSteel. So I modified these members, these beams to EGA 400, for example, and I modified some purling sections from hollow sections to IPA 180. Okay, so let's update the Tekla model with the update and Tekla structure functions. So in this case, we can update the Tekla model according to the whole ConSteel model, or just with the selected parts. We can export, in this case, also the grid and the connections, of course, if we have. And if you click on the continue button, model update is finished. ConSteel is updated the parallel Tekla model. If you go to the Tekla model, we can see the members are updated according to the ConSteel model. Okay. So now let's see what happens if we delete some members from the ConSteel model and make some parallel modifications on the ConSteel and Tekla model. So for this, I modify some members in Tekla structures, for example, EGA 200. Okay, and let's go back to ConSteel. I modify the same members parallelly. For example, EGA 400. Okay, and I delete some elements from the ConSteel model. Okay, and let's run again the update process. Okay, all of the members. Okay, so if you click on the update, the Tekla model functions, in this case, a new dialog appears. On this dialog, we can manage the merge conflict cases. In case of delete and parallel modifications, the user has to decide which status of the model, the ConSteel status or the Tekla status, should be used for the models. So on the dialog, we can say we can see each of the modifications. We have a ConSteel status column, Tekla status column. We can see the modifications. So these are the deleted elements, but it's unchanged in Tekla structures. And we have some. We have two members which were changed in Tekla structures, and we can see the parameters of it. So we can see the ConSteel parameters, the Tekla mode parameters. And if we have a lot of lines in the tables, so we have a lot of modified and deleted element, we can use these filters. So if it's needed, we can add some filters. For example, so it works like in Excel, for example. So we can use the filters options. And in the last column, we can decide which status we would like to use for the update, the ConSteel or the Tekla. And we have an extra options to see the selected line in ConSteel and in Tekla. So for example, if you click on one of the deleted elements, of course in ConSteel it's deleted, so it's not highlighted. But if you go to Tekla, so here you can see the selected element is highlighted in Tekla. Okay, and if you click on the update button, ConSteel is updated. ConSteel updated the parallel Tekla model. So here you can see the bracing system is deleted, and the beams was modified and updated according to the ConSteel model. Okay, so this is the new ConSteel and Tekla change management functions. Okay, so there is another function in the BIM, the link between the IDEA Statica and ConSteel, but it was introduced during the previous year, and the record of the webinar is published on our YouTube channel. So now I skip this function. So if you are interested in, so please visit our YouTube channel and you can find the previous webinar about this new link between the two programs. Okay, so the next big new function group or new tool is the seismic design tools. For this, I open a new model. So in ConSteel 11, the seismic design tools were completely redesigned and renewed. In the previous version, the previous tool had worked as a black box a bit. We were not able to check the different analysis result in the seismic analysis, and we were not able to control the process. In ConSteel 11, a completely new process was implemented to make the seismic analysis flexible and transparent. All of the phases of the calculation can be checked and controlled. Okay, so I have created a multi-story buildings. Slabs are represented with diaphragm. Now I have a simple loading system. I have a dead load, live load, snow load. Here you can see. And if you open the load case and load groups dialog, we can see it was a bit modified. We have changed the load group and load case field, so we have swapped. So the first field is for the load group, and the next field is for the load cases. And if we select one of the load case, you can see the convert to mass options was deleted from this dialog because it was moved to the completely new mass tab, where you can find all of the dynamic related functions. Okay, so we have a simple loading system with 3 different load cases. Okay, so let's go to the mass tab as a first step of the seismic analysis. So next to the load tab, we have a new tab for the masses and all of the dynamic analysis related functions. So in ConSteel 11, the loads and the masses are completely separated, and you are able to convert, of course, all of the previously created loads to masses, and you are able to place manually some extra masses on the structures if it's needed, and you are able to create independent mass combinations for dynamical analysis on this tab. And if we open the mass groups and mass case dialog, it's more or less same like the load cases and load group dialog, but on the left side you can find 3 structures. In the first one we can found the previously created load groups and load cases. With this checkbox we can automatically convert the created loads to masses. So if you click on this checkbox, ConSteel will automatically take into account the previously created loads as mass in the dynamic calculations. In the second 3 structures we can create some extra mass groups and mass classes if it's needed, and we are able to place and assign point masses to these mass cases. So in default we have a persistent mass groups, and we have a default mass cases, but if it's needed we can add some new mass groups, and we can add some new mass cases. And if you click on the OK button we can close the dialog. So let's place some extra point mass on the structures with the point mass functions. So in this case we have to set just the mass, so for example 1000 kilograms, and with a simple click, as in case of load structure, as in case of point structures, point load, we can place the mass on the structures. Okay. The next step is to create the mass combinations. So if we click on the Create Mass Combinations button on the Mass Combinations dialog, you are able to create several number of combinations. The new button, you are able to set independent mass combinations. The first columns is for the converted from load masses. So for the first one is the dead load, the converted dead load. Now I use with 1 multiplication factor, live load, snow load, and the last column is for the user-defined mass case, and we can create, if it's needed, another one. For example, okay. Spectrum and the seismic effect functions were also moved to the mass tab. So here you can find, and we separated the 2 functions, the previously in ConSteel 10 and the previous versions. These functions was implemented in 1 functions, the seismic effect and the spectrum, but from ConSteel 11 these functions was separated to 2 functions. So in this, we have create response spectrum functions, and we have a seismic effect functions. Okay, so let's create some spectrums. So the functionality is the same that was in the previous version. So we are able to create standard spectrums and user-defined spectrums, of course. So let's create the first standard spectrum. Okay, now I create with the default values. So you can select the type of the spectrum, the imported class, ground types, ground acceleration and vertical acceleration, of course, and we can see the horizontal and vertical effects. Okay. With the apply button, we can create the spectrums. If you click on the new button, we can create new user-defined spectrums, response spectrums, of course. We can create manually the whole spectrum, or we can clone as an existing response spectrum. Now we have just one standard spectrum, and we can create from this. Of course, in this case also we can set the ground acceleration and the vertical accelerations also. But in case of user-defined response spectrum, we have to set, so it is a design response spectrum, or this is an elastic response spectrum. It is needed for ConSteel. It is needed to know how can be handled the selected or the created spectrum. So that's why it is needed. So in the next field, we can edit the spectrum points. The spectrum can be same in all of the direction, or can be same in the XY directions and different in the vertical directions, or can be different in all of the directions in the horizontal, X, Y, and Z directions, vertical directions. Now I'm use the same in all of the directions, and I modified a bit the values of the spectrum. So for example, the plateau is the value of the spectrum on the plateau is 4. Okay, and this is a user design spectrum. And let's create a new one. And this will be an elastic response spectrum. And now I modified a bit the values. Okay, and this is a user elastic spectrum. Okay, and if you have mass combinations and response spectrum, we can set the seismic effect. Okay, so on the new seismic effect dialog, we are able to set the used mass combinations. So here you can find the two previously created mass combinations. So now I'm used for earthquake calculations for the mass combination 1. The next step is to select the calculation method. From ConSteel 11, we have implemented 3 different methods. The first method is the all mode with CQC submission. In this case, ConSteel takes into account all of the calculated dynamic shapes and summarized with CQC submissions. The next method is the selected mode with linear submission. In this case, ConSteel take into account just the selected dynamic shapes with the given multiplication factors and summarize with linear submission. So in this case, user has to select which dynamic shapes should be taken into account during the calculations, the seismic calculations, and multiplication factor must be given for each of the dynamic shapes. And the last method is the single dominant mode method. In this case, ConSteel use only just the dominant dynamic shapes in each of the directions. At first, I selected the all mode CQC method. The next step is to set the main direction of the structure, which will be the directions of the Q1, the behavior factors in the main directions, and the perpendicular directions will be for the Q2 behavior factors. In default, the main Q1 direction is parallel with the global x-axis, we can set the directions with 2 points with this black arrow button, or we can set the angle of the main directions from the X directions. Okay, the next step is to set the response spectrum. If you select the standard response spectrum, so now I'm using the standard response spectrum. So in this case, if you select the standard response spectrum, we can give the behavior factors in each directions. And if you consider the vertical seismic effect, we can set different behavior factors for the vertical directions. But if you use not standard design standard spectrum, but user-defined spectrums, Q factors are not necessary because in this case the spectrum must be contains the effect of the behavior factors. So that's why we have to select it is a design spectrum or an elastic spectrum on the settings of the spectrum. For SLS serviceability limit state calculations, we are able to use different displacement behavior factors. So here you can set the different displacement behavior factors, or we can select different response spectrum for SLS serviceability limit state calculations. So in this case, because if you select standard spectrum as a response spectrum for serviceability limit state, ConSteel use the standard spectrum as an elastic spectrum, so that's why the displacement behavior factor are not needed. And this is the method if you use user elastic spectrum. Okay, and we can check on the graphical area all of the selected response spectrum values in all of the directions what was set previously. Okay, and if you click on the apply button, we can create the seismic effect. Okay, so now we can go back to the load tab to create a seismic load group and create the load combinations. If you click on the load cases and load groups dialog, we can create, if you click on the new load group, we can create the seismic load group, and we can assign the created seismic effect for it. Because we have just one seismic effect, it's automatically assigned. Okay, and the last step is the load combinations. If you click on the wizard, you can create automatically the load combinations in seismic design situations for ultimate limit states and serviceability limit states. And if you can see, the load combinations dialog was also a bit redesigned. Ultimate limit states load combinations and serviceability limit states combinations were divided into two tabs to reduce the size of the dialog. So on the first tab, you can set the load combinations for ultimate limit states, and we can set load combinations for serviceability limit states. But I have made a mistakes, so you can see the considering accidental torsion effect is not available because I forget to set these options on the seismic effect dialog. So if you go back to so in this case we have to go back to the mesh tab and open the seismic effect. So you can see we have another tab where we can set all of the additional effects. So on the next tab, we can set which stories should be considered for accidental torsion effect and for second order effects analysis. So in ConSteel 11, the second order sensitivity according to the Eurocode is calculated, but for these calculations levels are needed. So that's why we have to create previously the stories and levels of the structures, and we can use these levels for seismic calculations if you click on the checkbox in the first column of this table. And the last step is to set the accidental torsion effect. So we can, the two combinations, the consideration combinations. So now I use the first method, and we can set the percentage of the accidental torsional eccentricity. Okay. Now I hope all of the settings are set. Full load combinations. Again, yes, now not just the load combinations, but the considering accidental torsion effect in the load combinations options is also available. Okay, so with these options, accidental torsion effects will be considered in the load combinations. And if you go to the sales visibility limit states, you can find also the load combinations in seismic design situations. And if you click on the checkbox and click on the apply button, ConSteel automatically create the necessary load combinations. In the second tab column, you can see the limit states. So here you can see which load combinations for ULS or SLS load combinations in seismic design situations. For ULS combinations, we can see the consideration of the accidental torsion effects. Okay, so the first three columns for the normal load cases. The last part of the table is for the seismic design situations. The first column is a general safety factors for the load combinations, so it can be modified automatically. But you can see we have three different directions, and the first main directions, the second main directions, and the vertical directions. And for the first main directions, we are able to set the alpha factors for the second order effects. If you leave on default, ConSteel will calculate automatically and use the automatically calculated alpha factors, or we can modify it manually if it's needed. So we can modify it to 1.5, or we can use the auto options. And here you can, in the next column, we can see the combination factors of the directions. So in this version of ConSteel used 100 plus 3000 submission of the different seismic directions. In some months, we will release a new ConSteel 11 service pack, which will contains not just with this 100 plus 3000 direction submissions, but the SRSS submissions also. But in this current version, just this 100 plus 3000 submission is available. Okay. We have created all of the load combinations. The next step is the analysis. So let's go to the analysis tab and let's open the analysis parameters. If we see the analysis setting dialog, we can see it was also redesigned to make it more clear and simple. So the previous tab system was deleted, so we don't have we have just one dialog. On this dialog, we are able to switch on and switch off the different analyses for all of the load cases and all of the load combinations. So here you can see the static analysis and dynamic analysis. So you can switch off and switch on all of the different analyses. But if you would like to make some detailed settings, you are able to click on, you can click on this arrow button, and you are able to set everything separately for all of the load cases and load combinations. So here you can see all of the load cases, load combinations, and you can set separately for all of the load combinations. So, and here you can find all of the other expert settings, for example, model portions for second order analysis, model portions for buckling analysis, or for example, the upper limit of relevant buckling eigenvalues. And we have an extra options for each of the analysis type. If you would like to reuse the running time or the size of the result file, you are able to switch off the unnecessary result for all of the different load combinations. So here you can find the different result type, deformations, beam results, shear results, plate results, reactions, and you can switch off these result types separately for all of the load combinations, or use these options. You can use the same settings for all of the load combinations. Okay. And if you click on the dynamic analysis fields arrow button, we can set some extra settings for response spectrum analysis. So here you can see our previously created mass combinations. So from ConSteel 11, dynamic analysis can be run just for mass combinations. So we can switch on with this with the first column with the checkbox. The first row is for the seismic analysis. In this case, you can modify just the number of the dynamic shapes what we would like to calculate, but the used design spectrum is fixed, so you are not able to modify it because it was set it on the seismic analysis, the seismic effect settings dialog. But of course, you are able to run independent dynamic analysis for the same load combinations if it's needed, and for another combinations, and not just the free vibration dynamic analysis available for the mass combinations, but you are able to run separate response spectrum analysis for another mass combinations also, for example, in this case, for the standard spectrums also. You can find the same result settings, and here we have some extra response spectrum analysis settings. So you can find the relative modal damping factors and the consideration of the modal shapes. You can consider all of the modal shapes, or you are able to set some minimum values for the effective modal masses in the different directions. Okay. And if you click on the calculations, ConSteel calculate the seismic effect, the response spectrum analysis, and all of the load combinations. So we have a new analysis report. So in this case, we have 3 tabs. If you don't have seismic analysis, load combinations, or response spectrum analysis, we have just 1 tab. This is the static analysis report. It is empty because we don't have any notes or warnings. In the spectral acceleration tab, we can see our spectrums, and we can see all of the calculated mass combinations. For the mass combinations one, we calculate the seismic effect with response spectrum analysis. So in this case, we can see the used spectrums separately for the ULS and from the SLS load combinations or design situations. And we can see the three different directions, and we can see the different calculated vibration modes, and we can see the type and then the used and calculated spectrum values in the different for the different vibration modes. Okay, and of course you can see the mass participations in all of the calculated mass combinations. We calculate independent free vibration for the mass combinations one, and we have seismic design situations, and we have an independent calculations for the mass combinations two. And here you can see all of the mass participations in the three different directions. And the last tabs, we can see the second order sensitivity. Here you can see ConSteel calculate all of the parameters and defined the alpha values, and we have a node. We have a nodes and descriptions, so the alpha factor is valid according to the Eurocode. And of course, and in this case, because the second order effect can be neglected, ConSteel use the one value for all of the load combinations. Okay, let's see the results. So we can see the results for modal response spectrum analysis in seismic design situations for ULS and separately for SLS. Of course, we have a summarized result. In this case, we can see all of the results summarized or with CQC method, with CQC submissions. We can see the three earthquake directions, the main one, the main two, and the vertical directions. We can see the deformations in the different main directions. We can see the normal forces from the seismic effect in the one directions. We can see the reaction forces, of course. We can see the accidental torsion effects. So in all of the directions, we can see separately all of the calculated results from the earthquake effect. But we can see not just the summed results, but we can see all of the results separated for all of the calculated eigenshapes. So we can see the eigenshape. So this is the eigenshape. So more or less the whole structure is moving in the x directions. In this case, we can see the calculated modal loads. Of course, it's not so transparent or not so user-friendly, because the modal loads is calculated for all of the node, but we can check it if it's needed. We can see the deformations, of course. So you can see, so this is the deformations, and of course, and we can see the internal forces and all of the reaction forces from all of the independent and calculated eigenshapes. And we can see the same results for from SLS design situations, because in this case I have selected a different response spectrum for SLS calculations, so that's why we have two modal response spectrum analysis and results. And of course we have dynamic results for mass combination 1 and mass combinations 2, so we can see all of the calculated dynamic results. So in this case we have ConSteel calculated just 3 dynamic eigenshapes, because this was the default settings. And of course we can see the first order, the calculated load combinations in for first order analysis. And if you see from top view, you can see, if you select one of the seismic load combinations, you can see how the structure is moving. In the different design seismic situations, seismic submissions. Okay, so these are the analysis results. Of course, we can run cross-section checks for CQC for seismic analysis. In case of CQC submissions, it is not possible to evaluate buckling checks because the CQC results are envelope results. But if you would like to perform not just cross-section checks for your calculation, but buckling checks also, you have to use the linear submissions or dominant mode calculations method, because in this case ConSteel calculate the summarized with linear submissions the seismic loads, and it is possible to calculate buckling modes, not just the internal forces, and deflections. So in this case ConSteel is able to perform the buckling analysis. So if you would like to calculate buckling analysis, we can go back to the seismic effect, and if you switch the calculation method to selected mode, linear submissions, for example, the apply button, you can set it. So in this case, so load group field is active, and we have a new button. So linear combination of modal effects. So of course in this case, so previously performed dynamic calculation is needed, but here you can see all of the previously calculated dynamic values and dynamic shapes, and just with simple multiplication factor you can set which modes you would like to use. And with linear submission, ConSteel calculate and summarize the calculated modal loads. Okay, of course, in this case, we have to recreate the load combinations. And if you go to the Analysis tab, okay, the dynamic, now I'm just calculate the first mass combinations, which is the seismic design mass combinations. And if you go to the static analysis, in this case, if you use linear submission or dominant shape calculation, we are able to perform buckling analysis for the load combinations. And if you click on the calculation button, ConSteel perform not just the first order and dynamic analysis, but the buckling analysis also in all of the load combinations in earthquake or seismic design situations. Okay, so it's ready. So we can see not just first order and modal response spectrum analysis is available, but the buckling analysis. So here you can see all of the buckling modes for load combination in seismic design situations. And if you go to the global checks, we are able to run buckling checks, not just the cross section check. Okay, here you can see. So the dominant examination is the global stability resistance. Of course, it's not adequate, but it's a simple example, so it's not a problem. But the buckling check is performed for in seismic design situations also. Okay, so this was the new seismic design tool. Let's go to the next topic, which is the csPI, the ConSteel programming interface. So for this, I open a new blank model. Okay, I close the previous model. Okay, so with the new csPI interface, parametric models can be built easily and run anytime. Any kind of ConSteel objects, such as members, plates, supports, loads, etc., and for loop and if-else statements can be used for parametric modeling. In the first, this is the first version of the csPI. On the base of it, we will develop a possibility of automatizations and user-created checks and macros with drag-and-drop user interface creator. So this is just the first step for further new functions, and I hope it's open some new possibilities for our users. Okay. So let's see. So csPI editor can be found on the bottom of the main windows on the left bottom corner with the arrow button. You can open the editor. It can be resized or undocked to a second screen. So csPI use commands and variables, cycles, and it can be found on our wiki page. So we have created a ConSteel wiki page, which can be found on the wiki.consteelsoftware.com. And here you can find all of the basics and all of the commands descriptions. So if you see the create command, here you can see how does it look like, and you can see all of the parameters. And for example, you can see the create member command. Here you can see all of the required parameters and all of the additional parameters with values and descriptions. At the end of all of the description, you can find a sample copy and paste code, and with a simple copy with Ctrl plus C and Ctrl plus V, you are able to copy to the editor, and with the play you can run the simple code easily, and you can see the member is created with all of the parameters. Okay, so let's study the wiki page of ConSteel and the csPI interface. But now I would like to demonstrate how can use it with a simple example. Okay, so let's create a simple column at first. So first of all, we have to load a section for it. So section can be loaded. Library sections can be loaded with the load section command. For example, ejs300. So this is the first command. And member, and let's create a member. Member can be created with the create command. We can add an ID if it's needed, or you can, so it's not a required parameters, but you can add an ID if you would like to use it for later. And it is a structural member, and the cross section is ejs300. Okay, so this was the parameters of the command, and we have some extra required parameters. The first required parameters is the coordinates of the start point and the coordinates of the end point. So, for example, and we have to set also the release at the start point and the end point of the member. So these are the required parameters for the create structural member of command. Okay. Okay, and if you click on the play button, csPI run the sort script and create the column. So here you can see. So this is a column with ejs300 sections, and the release at the start point and the end point is according to the short script, and the start point is start, and the global 000 and ends in the global 00 and 3000 points. And of course we can add some optional attributes if it's necessary. So we can add some eccentricities. In the y directions, for example. And in the z directions, we can set rotations. Okay. And if you run again, you can see the member is moved and rotated according to the settings. But not just members can be created with the create commands, but support also. So let's place a point support for this column. So it is a support point, and the type is fixed. and we have to set the coordinate of the point support. And if you run again the script, you can see the support is created automatically. Okay, but this short script is not parametric, because all of the parameters was set manually. So let's use some variables also. We can add some comments to make our script understandable for others. So this is start point parameters. Variables can be defined with this $sign. Okay. Okay, so this will be the height of the column. Okay. Okay, and if we modify the short script with these variables, okay, and if you click on the play button, you can see now our model is now it's parametric. And if we modified the parameters, for example, and run again, you can see we create a new column with the new parameters. Okay, let's use some cycles. For this, I add some new parameters. So this is the number of columns. So this should be the distance between the columns. Okay. Okay, and let's create a for loop. Our variables goes from 0 to the number of the column. And of course we have to close with end. And now if we run again, you can see the new model. Okay, so here you can see the new model. So we have 5 columns with 5,000 height start in the global origin. The distance between the column is 2,000 and the section is EJ 300. Okay, and this short script can be saved for later use. So the csPI script is saved for in a different ConSteel file, so it's not saved in the ConSteel model. So this csPI file can be sent to another user, and we can load later a previously created file, of course. And how can we use csPI in a real project? So let me show you an example. So this is a 3D complete hole with tapered frames. So here you can find the parameters. So here you can see the span. So now it is 2,000 millimeters. 20,000 millimeters. So now I modified to 3,000 millimeters. The distance between the frame is 6,000, but we can modify it to 5,000 millimeters. The column height, we can set the column height, for example, 5,000 millimeters. The apex height, the top height is, for example, 10,000 millimeters. The number of the frames set for 10 for the holes. And in this example, the model is created with tapered members, and the parameters of the tapered members also parametrically can be modified. So, for example, the end height of the beam now I set for 10,000 millimeters. And if you click on the play button, csPI create automatically, sorry, it was the previous model. So csPI create automatically the parametric model according to the settings. But if we click on the shear, the load transfer visibility, so you can see not just the members and the support was created, but it was covered with load transfer surface. And if you go to the load stubs, you can see 2 load groups and load cases was created, and 2 simple load cases was created by the csPI script. The first load cases contains some point loads, and the second is contains 2 uniform surface load. And if you see the member, you can see the end height is 1,000 millimeter as setted, and the column height is 700 millimeters as was the default value. And you can see not just the frames, but the purlins are modeled eccentrically, and the purlins is connected to the frame with link elements. And you can see the bracing system is a simple bracing system. Element types is automatically setted for tension bar. So this is a real project. So if you are dealing with same structures and you are able to handle with parameters, so it is a very easy way to create this kind of scripts, and you can create parametric models anytime. So this is the csPI interface. Okay. Let's see the other minor functions in ConSteel. So there are several minor new functions in ConSteel 11. such as new section types for convert to plate functions. We have some new standard macros. With these macros, you are able to create your own standard sections, not just the welded and cold form sections, but now the standard sections are also available as macro sections. We have some new standards. For example, the complete Italian code is implemented, and we have implemented the Spanish seismic code also, and the new Eurocode national annex is also implemented, and we have some new maps for wind velocity and seismic ground accelerations, etc. So there are several minor new functions, but now I would like to show you and present you some two new functions: the shear field calculations and the improved frame corner result. So let's start with the shear field calculations. For this, I open a simple model. So the shear fields are used in daily practice in Germany. In German for the design of structures by considering the stabilization of effect of the trapezoidal decking connected to the bar element. So with these new functions, you are able to take into account the shear stiffness of the trapezoidal sheetings in the buckling calculations. So at first, let's run a buckling analysis to see the difference between the So this is the original model without shear fields. So here you can see the buckling eigenvalue is 2.26. So let's go to the structural member tabs where the shear field function can be found. So here you can find the shear field functions. The stiffness value can be set manually. So if you have the value, you can set manually, but with the 3 dot buttons, you are able to select and use one of the included trapezoidal sheets, so the trapezoid sheets. So in the new button, you can create a new shear field stiffness calculations. So I have previously loaded Fisher sheetings, but with the 3 dot button, you are able to load any kind of included sheetings. So here you can see all of the sheetings, and you can see all of the parameters which are needed for the calculations. Okay, and if you load the sections, you can see the calculation method, because every producer specify a method for the calculations of the stiffness. So that's why it is highlighted or shown. Okay, so now it is loaded, and the applied calculation is the producer defined calculations, and of course you can use the general Eurocode methods if it's needed. Okay, and here you can see the properties of the shear field. So you can set all of the needed parameters. Of course, the parameters is depend of the selected calculation method. So we can select in this case the fixing. So the sheetings can be fixed in each ribs or each second ribs. The shear panel X is the physical length of the shear panel. So it could be the whole length of the hole, if it's the whole roof is created as a shear field. So it could be 60 millimeter, for example. Fixing distance is the distance between the fixings parallel the directions of the sheetings. So for example, so this is the value. Okay, and everything is set it with the apply button. You can create the shear field calculations, and you can see the stiffness is automatically calculated. The effective width in general case is the distance between the frames. So for example, it could be 6 millimeters. Okay, and the shear field can be placed to the reference line, or eccentrically or with eccentricity to the bottom or to the top, and it could be placed on the whole length or just as a partial on the partial length of the model. And with a simple click, we can place the shear field stiffness on the model. You can see, so this symbol is show us that the shear field is placed on the model. And if we go to the analysis, we can see the effect of the calculation. So here you can see the buckling eigenvalue is significantly higher, so it is 3.34. So this is the shear field calculations in ConSteel 11. If you need more information about the shear field calculation, you can find a post on our ConSteel blog about the different methods, and you can find simple calculations. So if you go to the ConSteel blog, consteelsoftware.blogspot.com, you can find our latest post is about the shear field calculations. So here you can see all of the different methods with some explanations, and at the end there is a small examples about the calculations. Okay, so let's go back to the new functions. One of the last function is the frame corner wizard. So the new function is the improved frame corner wizard. So of course, frame corner wizard was available in the previous version of ConSteel. With these functions, you can take into account the structural behavior, the different structural behavior in the frame corner zone. But with the improved frame corner functions, not just the behavior of this frame corner zone can be taken into account in the calculations, but the connection topologies also can be considered in the calculations. Okay, so we have a simple model, and if you go to the structural member tabs and click on the frame corner wizard options, you can see a new dialog with the on-off button. You can switch on the frame corner wizard. In general, ConSteel uses the default type, this gray type. So this was used or available in the earlier version, but now we have 3 more options. So the next one is the box type stiffened, bolted or welded type. The next one is the bolted or welded with diagonal end plate, and the last one is the box type stiffened, bolted or welded with additional 1 or 2 diagonal stiffeners. And you can, and if you click on it, the apply button, you can assign for the structure. If you need more information about these functions, you can click on the more information button, and here you can see some descriptions about the joint topology, about the warping transfer, and the frame corner zones considerations. And we make some verification to compare the results with the Shear models. And we found that the results are very close to each other. So now I would like to show you. So these diagrams show the results of B model with diagonal box joints to the results of the reference Shear model for different column beam ratios and different slopes and supports configurations. And you can see the results is very close to each other. Okay, so this is the frame corner wizard options. Okay, so let's see the new functions of the csJoint model as our last topics in our webinar. So let's see the new functions. At first I would like to show you the automatic joint update. If we have placed structural joints on the structure and we modify the structural model, now ConSteel warns us that the joint must be updated according to the actual ConSteel model. So for example, in our model we have placed structural joints. It is a simple beam to column connections with templates. And if you modify, for example, the sections of the column for a bigger one, ConSteel automatically warn us then that the joint module, the joint must be updated, and if we select the joint, you are able to update the joint module. Okay, and if you see the place joint, so the column is automatically updated, and you can see our joint model is according to the actual ConSteel model. So this is the new automatic joint update. So let's see the improvements in the joints types. Okay, so in case of hollow section joint from csJoint 11 and ConSteel 11, we are able to use joint stiffeners, so we can reinforce the joints. In case of joints between hollow section braces and I or H cord, we can apply core stiffening. So here you can see. And of course, we can set the thickness of the plates, and here you can see, and the calculation is automatically according to the stiffenings. So here you can see the core stiffenings options. In case of hollow section braces and hollow section joints, we can apply both web stiffening and flange stiffenings also. So here you can see. And of course we can set the thickness of the plates, and the joint check calculation is according to the reinforcement. Okay. And finally, pin-based connections from these versions, not just tube and I or H cross sections can be used, but hollow sections SHS hollow sections can be used also. So here you can see. So in this case, the 4 bolts configurations can be used. You can set the bolt configurations. You can set the thickness of the plate. Yes, and here you can use, and you can use this kind of joints also for hollow sections. Okay, so for now I'm done with my presentations. So about upcoming webinars and events, etc. You can find more information on our website, ConSteel.com, consteelsoftware.com, and follow us on our social media sites to stay up to date with ConSteel. And I would like to draw your attention on our YouTube channel, where you can find lots of videos about the new functions and existing functions, and you can find the previously recorded webinars also. And you can contact us on our email address or directly call us if you have any questions or comments. So I would like to thank everyone to attending our today webinar. I hope you enjoyed and learned in this presentation, and see you on our next webinar. So thank you very much, and goodbye.